Hello students, welcome to Akshara 8 Foundation. So today we are going to continue the last concept. We are doing the moment of inertia of the regular shaped bodies. So we have found their moment of inertia of a circular ring, circular disc about the axis passing through its center, and we have found the moment of inertia of the ring about the axis passing through its center and perpendicular to its plane. Okay. So then today we are going to see there some more theorems. So by using that we can find out the moment of inertia about any axis. Okay. So then there are the two theorems are there. They are very important theorems. Then after finding that theorems, then we can find out the moment of inertia of the different bodies about any axis there. Okay. So that theorems we'll see now. So first one, perpendicular axis theorem. Perpendicular axis theorem. Perpendicular axis theorem. So what the perpendicular axis theorem says? So suppose let us consider this is a rigid body. So this rigid body is rotating about this axis. Consider there. So now if we consider here two mutually perpendicular axes, so the moment of inertia about this axis which is perpendicular. Consider here this is a z axis there. Okay, and we'll consider this is a x axis, the moment of inertia about this x axis, and here we'll consider that this is a y axis there. Okay, that we'll consider here y axis. Okay. So now here the perpendicular axis theorem will says that according to the perpendicular axis theorem, the statement of the perpendicular axis theorem, the moment of inertia about any axis, is equal to the sum of the moment of inertia about the mutually perpendicular axis. Okay. So see here, suppose the moment of inertia about the z axis will be equal to the moment of inertia about any axis is equal to the sum of the moment of inertias about their mutually perpendicular axis. There is the statement of the perpendicular axis theorem there. So now you consider there here this is a moment of inertia about the x axis, and this is a moment of inertia about the y axis there. So now here we can add there, according to that statement, the moment of inertia about this axis, z axis, will be equal to the moment of inertia about x axis plus the moment of inertia about the y axis. Moment of inertia about the x axis and moment of inertia about the y axis there. So how to find out this one? So we can find out by using here this one. So this is x axis and it is a y axis now. By applying the Pythagoras theorem, we can find out their moment of inertia about the axis there. So suppose if we consider there, this is a x axis, the moment of inertia about that this x axis can be taken as here. So here we can add there the moment of inertia about x axis. So here we can add there moment of inertia about x axis can be written as here. So m into capital M into, this is the mass of the body, and here we can add the distance from here there. So let us consider the distance from here. If you take here the distance from here, let us consider here at a distance x distance. Suppose here you consider there this is a from here to here. Consider, so this is the y axis, this is the y, and this is the y coordinate, and here it is the x coordinate we can consider there. Okay. So now the moment of inertia about this axis of this particle, we can add here m into x square, we can add there m into x square. Then moment of inertia about the y-axis we can write here capital M into, so y square we can write there, y square. Okay. So if you apply here the Pythagoras theorem, if you apply the Pythagoras theorem there here, so what can we get there? Moment of inertia about the z-axis. The moment of inertia about the z-axis can be written as here. So then that can be, so now here yz can be written as here m into z square we can write there, m into z square. Now here, so from this we can write here, and this will be the, this distance will be the z coordinate, it is z square. Now by applying here Pythagoras theorem will get there, z square is equals to, so x square plus y square will get there. Now here z is equals to, so z square is equals to x square plus y square. Now here if you multiply here m into z square is equals to m into x square plus m into y square we can write there. So m into z square is nothing but what there, moment of inertia about the z axis. So we will write here, that is, so the moment of inertia about the z axis will be equal to the moment of inertia about the x axis plus moment of inertia about the y axis. So this will be the perpendicular axis theorem. That will be the perpendicular axis theorem there. Okay, by applying the Pythagoras theorem, we will get it there. So the moment of inertia, perpendicular axis theorem, or statement of perpendicular axis theorem is, the moment of inertia about any axis is equal to the sum of the moment of inertia about their mutually perpendicular axis there. Suppose if we consider the moment of inertia about this z axis, then it is the sum of the moment of inertia about this x axis and the y axis there. Suppose if we consider the moment of inertia about the x axis, that will be equal to the moment of inertia about the z axis and the moment of inertia about the y axis there. So that we can find out there. This is a perpendicular axis theorem. Perpendicular axis theorem. So next one we have the parallel axis theorem. Next one we have parallel axis theorem there. Okay. So second one, parallel axis theorem. Parallel axis theorem. Parallel axis theorem. Parallel axis theorem. So according to this theorem, parallel axis theorem will says that, suppose the moment of inertia about any axis if you want to find out there. Okay. So that moment of inertia about any axis, suppose let us consider this will be the moment of inertia about the axis passing through its center of mass. Axis passing through its center of mass. So let us consider the moment of inertia about this axis, it can be written as here I naught. And if I want to find out the moment of inertia about any parallel axis to this one, suppose I want to find out the moment of inertia about that axis there. So about this axis. So like this, about this axis I want to find out. Then in this case, it can be considered as the moment of inertia about the parallel axis. This is the moment of inertia about this axis. Okay. So now the moment of inertia about that axis, the moment of inertia about any axis which is parallel to the moment of inertia about the center of mass, which is passing to the center of mass. So that can be equal to, okay, the moment of inertia about any axis is equal to the sum of the moment of inertia about the center of mass and the product of mass of the body and the square of the perpendicular distance. Suppose if we consider here the perpendicular distance from the axis of rotation from here to here, if we consider this distance is r and mass of this particle is here, mass of this body can be written as here capital M. So then the moment of inertia about any axis which is parallel to the moment of inertia about the axis passing through the center of mass plus the product of mass of the particle, mass of the body and the square of the perpendicular distance. Okay. The moment of inertia about any axis is equal to the sum of the moment of inertia about the center of mass, sum of the moment of inertia which is passing through the center of mass and the product of mass of the body and the square of the perpendicular distance. Okay. Square of the perpendicular distance between the axis there. So now here we can write this one I naught plus so product of mass and square of the perpendicular distance. So that can be written as here r we have considered there. So r square we can write there. So this will be gives the parallel axis theorem. That will be gives the parallel axis theorem. Suppose any axis about any axis which is parallel to this moment of inertia about the axis passing through the center of mass. So now here we consider the parallel axis which is passing through the center of mass. So moment of inertia about this axis will be equal to the sum of the moment of inertia about the axis passing through the center of mass and the product of mass of the body and the square of the perpendicular distance between the axes. So that is called the parallel axis theorem. So now by using this we can find out the moment of inertia about any axis. So yesterday we have found, in the last class we have found there, the moment of inertia of a ring we have found there. So that about the axis passing through its center and perpendicular to its plane we have found there. So we got there mr square. So I is equals to mr square we can find out there. Now by using this parallel axis theorem and perpendicular axis theorem, so we can find out about any axis. Okay. Suppose if you want to find out the moment of inertia about the ring, and the axis which is parallel to this parallel to the axis passing through the center and perpendicular to its axis. So suppose if the moment a body is traveling like this, the moment of inertia about the axis passing through its center and perpendicular to its plane, then so if you want to find out the moment of inertia about an axis parallel to this axis which is passing through the center of mass. So for that we can find out now here the parallel axis theorem there. So the moment of inertia about this we got there now. That is what we got there, mr square we got mr square. Now if you want to find out the moment of inertia about this one, about this axis, moment of inertia about this axis means, so how to find out there now? So let us consider this is I1. So I1 can be written as here, I1 is equals to I0 plus mass of the body it is m, and this is square of the perpendicular distance. So here distance is what there, r only, no, radius only, r will be the radius only. So we can write here mr square. So now here what can we write there now? So I is what we got here, this one, I is equals to I1 is equals to the moment of inertia here, we can write here mr square plus mr square, we can write there, and it is perpendicular to its axis. See, perpendicular to the plane there. So perpendicular to the plane means this one, the distance between these two axes we can write here mr square. About this axis it has to be rotated now. So that is the moment of inertia about the axis passing through its center perpendicular to its plane, and this is the moment of inertia about this axis. Here we can add there I is equals to I0 plus mr square we can add there. So the distance between these two axes is mr square we can write here. Then I1 is equals to, we can write here 2 into mr square we can add there. I1 is equals to 2 into mr square. Okay, the moment of inertia about the axis. So that is the advantage of this theorems there. So by using this parallel axis theorem and perpendicular axis theorem, we can find out the moment of inertia about any axis. Okay, so now we'll see there one by one. The moment of inertia about the moment of inertia about the diameter of the ring there. Okay, so we'll see the next one, the moment of inertia of a ring passing through its the moment of inertia passing through its the moment of inertia of a ring, axis passing through it ring about an axis passing through its center along the diameter. Okay. So the moment of inertia about an axis passing through its center along its diameter. Suppose let us consider this is a ring here. It is the ring, and we know that the moment of inertia about this axis, about the axis perpendicular to its plane and passing through its center, that we got here I naught is equals to mr square. We got there I naught is equals to mr square. So now they are asking the moment of inertia, it is passing through its center along the diameter. Now the moment of inertia about this we should find out there. Okay, the moment of inertia about this axis. So now here we can write there, this is the z axis, and now moment of inertia about this as also we can write there, these two are same, no? So the moment of inertia about this is, we can write here Ix, and the moment of inertia about this is Iy there. So it is the moment of inertia about the diameter, it is same there. Okay. So now according to the perpendicular axis theorem, the moment of inertia about the z axis can be written as here, the moment of inertia about x axis plus the moment of inertia about the y axis there. So these two will be same there, no? It is, they are the diameters. So we can write here, from that Ix is equals to Iy we can add there. Then Iz can be written as here, Iz is equals to 2 times of Ix we can write there now. Then Ix can be written as here, Ix is equals to Iz by 2 we can write there now. So that is here mr square by 2 we can write, mr square by 2. So now the moment of inertia about the axis passing through its center along the diameter. So we can write here, that is mr square by 2. So even it is equals to the moment of inertia about an axis passing through its diameter along the y axis also we can write. So this is also, it is equals to Ay. So this is the moment of inertia. So this is advantage of parallel axis theorem and the perpendicular axis theorem there. By using the parallel axis theorem, perpendicular axis theorem, we can find out the moment of inertia about any axis. Okay. Clear now? The moment of inertia of a ring about an axis passing through its center along the diameter. So along this diameter there, that we can consider along the x axis, and this we can consider along y axis, and this is along the z axis, that is passing through its center and perpendicular to the plane of the ring. That is the z axis we can consider. So then we can add here the moment of inertia about that axis, about the diameter, we can add there here mr square by 2. So now even we can find out like this. So next one, the moment of inertia about the axis along the tangent. The moment of inertia about an axis passing parallel to the moment of inertia parallel to the moment of inertia about axis passing through its center and perpendicular to its plane perpendicular to its plane That means what there? So suppose if it is a ring here, that is the ring, and now we know that the moment of inertia about the axis passing through its center perpendicular to its plane there. So this we know that is I is equals to mr square will write here. So now about this, the moment of inertia parallel and it is passing through this line parallel to this one there. Now the moment of inertia about this one we should find out there. Okay, the moment of inertia about this one. So now this line is it is, suppose this is a ring there, it is the ring there. Now moment of inertia about this mr square will be there because it is passing through its center and perpendicular to axis there. Now the moment of inertia about this axis, so it will be rotated like this. It will be rotated about this one. Now the moment of inertia about this, to find out here, these two axes are parallel axis. So now we should apply here parallel axis theorem. So now here we can write their moment of inertia about this axis. The moment of inertia about this axis, let us consider this I1, that is equals to, here we can add there I0 plus, so mass of this one, and here, so mass of this one, mass of the ring is m, and the square of the perpendicular distance. Square of the perpendicular distance means here, so the distance between these two, it is, this is a radius only we can write now, radius r only we can add there, the distance between the two axes, that is r only. So we can write here r square, m into r square we can add there. So now the moment of inertia here I1 can be written as here I1 is equals to mr square plus here mr square we can write. So then I1 can be written as here 2 into mr square we can write there, 2 into mr square. This is a moment of inertia about an axis passing through its tangent perpendicular to its plane, tangent perpendicular to its plane. Now the moment of inertia about the tangent, the moment of inertia about the tangent we can write there here. So that how to find out there? Is it clear now? Now the moment of inertia of the ring, the moment of inertia of the ring, the moment of inertia of the ring about its tangent, So tangent means it is like this. So now if this is a ring here and the moment of inertia about this axis, it is perpendicular axis. Now the tangent is nothing but here. So exactly it is like this about this axis. The difference is here, it is like this. This is the moment of inertia and the tangent means this is the tangent there. So the moment of inertia about this axis means it will be rotated like this about this axis there. So now here these two are the perpendicular axis. So this is a perpendicular to this axis there. So now we can consider the moment of inertia about this axis now. So it is this one we can write here. Y axis we can write there. Okay, and this one we can write here x axis we can write there here. This is a x axis, Ix. Okay, so now this one will be the z axis we can write there here. Now the moment of inertia about the z axis is equals to the moment of inertia about x axis plus and moment of inertia about the y axis. So then moment of inertia about the x axis and the moment of inertia about the this one. This will be the moment of inertia about this one now. So here it is the perpendicular line now. This is about the diameter now. The moment of inertia about x axis is nothing but it is the diameter. So now the moment of inertia about the diameter we got there how much? That is we got here about x axis. So this is about x axis no diameter. So we got that is mr square by 2. So now plus this is a moment of inertia about that axis here Iy we can write there. And now the moment of inertia about the z axis we can write here mr square. Okay, mr square we can write there. Now here the moment of inertia about this tangent, so we can write here Iy is equals to the mr square minus mr square by 2 we can add there. So therefore we'll get here the moment of inertia about this axis will become here mr square by 2. So mr square by 2. Mr square by 2. So therefore the moment of inertia about the tangent Iy can be written as here mr square by 2. Mr square by 2. The moment of inertia about the tangent, along the tangent we can write here mr square by 2. Mr square by 2. Clear? Now the moment of inertia about the circular plate. So in the last class we have found there the moment of inertia about the circular plate passing through its center perpendicular to the plane we have found there. So now we will apply this parallel axis theorem and perpendicular axis theorem so that we can find out the moment of inertia about the moment of inertia of a circular plate. About its tangent we can find out there, okay. The moment of inertia, the moment of inertia, the moment of inertia, the moment of inertia of the moment of inertia of a circular plate or a disc, circular plate about its tangent, about its tangent, about its tangent. So circular disc. So this is a circular disc we got there. This is a moment of inertia about the axis passing through its center and perpendicular to its plane. So that we got here the moment of inertia about that axis here I naught we can write there. So mr square by 2 we got. Mr square by 2, no? That we got mr square by 2. Now along the tangent means along like this. So it is about like this, about this axis there. Okay. So the moment of inertia about this one, about that axis there. Now here this is a perpendicular axis to this one. Okay. So means it is a circular disc. And this tangent means the moment of inertia about this axis there. So it is like this tangent. The line, okay, at any point, the line drawn in a curved point. The line drawn in a curved point is nothing but the tangent, no? So now this is the tangent there. It will be passes perpendicular to this axis, perpendicular to the axis there. So now how to write this one perpendicular to the axis? So before going to this one, we can do here. Suppose this is a moment of inertia about its diameter. Suppose if we consider there, and the moment of inertia about this one, or this one about y-axis. Okay. So now this one, the moment of inertia about this axis, the moment of inertia about this axis. So here we can add there. It is the consider this is the moment of inertia about the x-axis and this one will be the moment of inertia about the y-axis. The moment of inertia about the y-axis and this will be the moment of inertia about the x-axis. Now if you write there this one Iz or this is equals to I naught or Iz. Iz is equals to we can write here the moment of inertia about x-axis plus the moment of inertia about the y-axis. Those two will be same because they are traveling. Means the line is traveling, both are mutually perpendicular and they are passing through the diameter. So we can write here 2 into Ix or Iy, Ix or Iy we can write there. So now Ix can be written as here, Ix is equals to Iz by 2 we can write there, Iz by 2. So Iz here, Iz or I naught. So this is Iz now, Iz or I naught by 2 we can write there. So that we can write here mr square by 2 divided by 2 will be there. So we can write here Iy or Ix is equals to, we can write that is mr square by 4 will get there, mr square by 4, mr square by 4. So now the moment of inertia, now about this axis, the moment of inertia about the tangent and the moment of inertia about the x-axis. Okay. So now here the moment of inertia about this axis to find out there, this is a perpendicular diameter will be, this diameter is perpendicular to this axis, and this one, it is perpendicular to the line which is passing, here, this is perpendicular. Now the moment of inertia about this axis is perpendicular to this one, no? So we can write here perpendicular to this one, and it is a perpendicular to this one. So we can write here mutually perpendicular. So now the moment of inertia about this axis. So let us consider the I naught. I naught can be written as here moment of inertia about the z axis plus the moment of inertia about x axis. The moment of inertia about x axis. Now the moment of inertia about that axis can be written as here. Iz is how much we got there? Mr square by 2 plus here mr square by 4. Mr square by 4. So now here we'll get there 4. So we can write here 3. So 3 mr square by 4. So 3 mr square by 4. So I1 is equals to, this is the answer we'll get there. So this is what there, the moment of inertia about the tangent. The moment of inertia about the tangent of a circular plate along its tangent. The moment of inertia about a tangent of a circular plate, about the circular plate. Okay, this is a moment of inertia about the tangent. So now the moment of inertia about its diameter we got there, mr square by 4 of a circular disc. Okay, so these are the some of the cases of the applications of parallel axis theorem and perpendicular axis theorem. So in the next class we are going to do their numericals on these problems, and I'll give the list of different moment of inertia of the different bodies about their different axes. Okay, so by using that table we can do any type of problems based on this moment of inertia. Okay, thank you children, have a nice day.